Excited to be hosting Dr. Agustinus Kristiadi today. Um, Dr. Kristiadi is a postdoctoral fellow at the Vector Institute and previously obtained his PhD from the University of Tübingen in Germany. His research interests are in probabilistic inference with large-scale neural networks, decision-making under uncertainty, and their applications in broader scientific fields such as chemistry. His work has been recognized in the form of a Best PhD Thesis Award and multiple spotlight papers from flagship machine learning conferences. In addition to his research, his contributions to the broader scientific society include mentoring underrepresented students in Canada under the IBET PhD project and actively contributing to the open source community. Okay, and Dr. Kristiadi's talk's title is Probabilistic Inference and Decision Making with and for Foundational Models. Promises to be quite exciting. Okay, over to you.
All right, thanks very much, Ruth, and happy to be here. Nice to see you here. And yeah, it is my pleasure to be here, and I'm going to talk about topics that's kind of relevant for today's standard, and hopefully you enjoy it while you're enjoying your meals, okay? So today I'm going to talk about probabilistic inference, especially Bayesian inference, and especially for making decisions in foundation models, all right? So without further ado, let's go to the first slide, which is thought experiments. Okay, so the thought experiment is like this: should I bring an umbrella or not today? So imagine yourself, sorry. So imagine yourself at home, right, in the morning. You haven't seen the outside yet, and then you want to decide whether you should bring an umbrella or not. Well, you might think about it like this, right? So you might think that, oh, usually it's sunny this time of the year, so maybe I shouldn't bring the umbrella, right? Because it's bulky and so on. But actually, when you look at your phone, you see the weather app, it says that it's 80% raining, right? Oh, then I have to, reweigh my judgment here about the action that I take, whether I should bring umbrella or not. But then you also have preferences, right? So your preferences might be that you want to avoid being wet at the office, right? Or maybe umbrella are just bulky and it's not worth your carrying capacity, basically, right? And then based on those things, we can make decision. Okay, so maybe if you consider all these cases, then maybe you will bring the umbrella anyway, right? So what are these things? These are the first one here is a prior. It's a prior belief, right? This is encoding our experience, encoding our knowledge about the past, and in general about what you learn from the world from the previous time. And then this is an observation, right? Because it's a new observation from about the state of the world. When you look at your phone, that's what you get. And then you can combine them together to get the posterior belief, right? So it's a belief about the state of the world or about the unknown. And what is the unknown here? Whether it will be raining or not, right? When you condition your belief with the observation, that's relevant for that unknown, right? And this is called the utility function, which encodes your preferences given the unknown and given the action that you will take. And combining them together, you will get your decision or action. So in mathematical sense, what we are doing here is actually doing probabilistic inference or Bayesian inference. I will talk about, Bayesian inference is equivalent as a probabilistic inference in this particular talk, right? So if you hear probabilistic inference, that means Bayesian inference. So yeah, you know Bayes' rule, but the thing that's to note here is it's not just probability, but there's some philosophical meaning about it, which is prior belief, P of F here. F is the unknown, whatever it is, right? And then this is your observation encoded in the likelihood, where D is your set of observation, and then this is your posterior belief, okay? And then the decision-making framework that we have seen before is basically encoded by this equation, which is the Bayes decision rule, basically, right? So if you have an unknown, and then you have a belief about the unknown, and then you have the utility function, then the optimal action would be taking the maximum, the action that maximizes the expected utility function, right? And what are the applications for this? Well, materials and drug discovery, as we will see later in the first half of the talk. For safety, for example, you can think about it in terms of, for example, detecting out of distribution data and so on and so forth, right? And the interesting part here is that if we have belief that is miscalibrated, for example, your belief is overconfident and wrong, then you will make bad decision, right? Just imagine if you believe that it's okay to rob a bank, right, which is obviously wrong, and then you believe about this very strongly, let's say 99% confident, right? And then by the time you want to make an action, oh, I'm kind of bored, what should I do? Well, if you have that kind of belief, then you will rob a bank, right? So miscalibrated belief implies bad decision. So the question here then, can we improve our beliefs via foundation models? Because foundation models are super large and so on and so forth. We will talk about it later. So that's the main principal question that we will talk about in the first half of this talk. And in particular, I'm going to talk about our paper that just presented at ICML this year, and it is about Bayesian decision-making in chemistry, especially for materials discovery and drugs discovery, okay? So what is a material discovery problem? So it's basically a super simple problem. So it basically just poses this question. Which molecule X maximizes probability f of X? Molecule could be anything, right? H2SO4, HCl, or some kind of crazy compounds, whatever it is. And then f of X, what would be f of X? Well, it's up to you, right? For example, it could be if you make a new battery technology with this molecule, what would be the energy efficiency, right? That would be f of X, right? Or if you want to create a new drug, for example, if I use this molecule to make this drug, then what is the efficacy of this drug? So that's also f of X, right? So it could be anything. And in fact, this is how we do technological advance, right? So if you look at your phone or your laptop, for example, your screen is most likely OLED, right? So organic LED. So it's composed of organic molecules. And that's how people actually advance the technology of screens, right? So you want to find new organic molecule such that, let's say, the screen would be brighter than before, right? So that's f of X, all right? So it's very important in technological advances. And the way we, or rather chemists, not me, do this is that they have a set of molecules called the virtual library. And it's a really large set, actually. It's just not infinite, but it's kind of large. So this is a set of molecules that we know we can synthesize, right? So because we need to synthesize the molecule, meaning that we create the molecule first, and then we use it for something that we care about, for example, making the screen, right? So we have these candidate molecules in a giant list, and then the properties here is something that we want to uncover, and we want to find the molecule X that maximizes this property. But of course, it's very hard to do, right? Because you cannot just do exhaustive search because the number of such molecules is very large, and then you have to make the screen or the battery at every time you pick the molecule. It's very labor intensive and it's very expensive, right? So one way to approach this problem is to create a data set D, right? So for example, you just pick whatever molecules like 2, 3, 4, 5, right? And then just do lab work for those 5 molecules. And then you get the properties, like initial data, essentially, right? And then you fit a surrogate function. Surrogate function is basically a posterior belief about the unknown, right? So what is the unknown? Well, the unknown here is the property F, right? So that's why we have a surrogate function of the unknown over all the molecules in our virtual library, right? So here now we have a prediction and also the uncertainty around it, right? And then we make a proposal, right? So which molecule should we try next in the laboratory setting, right? In that case, we realize again on the Bayesian decision-making equation that we have seen before, right? Just take the expected utility function under which whatever utility that you want to use. and if you know Bayesian optimization, then it's basically usually it's being condensed together into the so-called acquisition function, right? And then you do the experiment, then you get new data point, right? And you append it into your data set and rinse and repeat. So this is the principle of Bayesian optimizations, okay? And this is the pseudo code that I just mentioned before. And the standard workflow in Bayesian optimization is that you work in the vector space, right? So you have molecules that's represented by, like a smile string or graphs or whatever, and then you transform into features like a point in Rn, let's say, right? And then you just do standard regression with Bayesian flavor on top of it. Let's say using Gaussian processes or Bayesian neural networks can also be used here, right? But the problem would be, how can we actually represent a molecule for Bayesian optimization? Because imagine that if your representation is not that good, then of course your belief would also be bad, right? And as I mentioned before, bad belief, badly calibrated belief implies bad decision. And in the case of natural discovery, there is no catastrophic problem at all, but it will make your experiment much more expensive, which we want to avoid, right? So for example, if the molecule is represented with a smile string like this one is H2SO4, and then we can use a text encoder or whatever it is, right? Or using a string kernel in Gaussian process. If we represent the molecule as a graph, then we can use graph encoders or graph kernels in Gaussian process, right? But it's unclear, right? We have to try all of this, and then it's just like a hyperparameter for us, right? So can we actually is there one solution that fits all, right? So that's the question. Well, we are in the age of LLMs, right? So LLMs are kind of, interesting because they seem to know a lot of things, right? So if you ask the LLM here, for example, what is the molecular mass of this smile string H2SO4, right? Then they seem to be, knowledgeable about it. Kind of close, but wrong, right? Should we just ask the LM to be, the experimenter instead of, doing this standard Bayesian optimization? Well, not so fast, right? So in here, I revise the question and then ask also the confidence level, which is important because we care about beliefs, right, to make decision. And here, they are wrong. They produce incorrect answers, and they are mostly very, very confident. All right, so this is bad. And if you do Bayesian optimization with this kind of belief, then yeah, you're not getting anywhere. All right. So that's the problem with LLMs today, because it's just so general purpose and so on and so forth. But I'm not saying that LLMs are bad, but we need to harness LLMs. That's the knowledge that encoded in the LLM. What we need to do is to see LLMs as they are. And what are they? They are ready-made models, right? Encoding information from the pre-training data that's very, very huge, right? Even like the whole internet, right? So what are those? If we put our Bayesian hat on top of our head, they are prior beliefs, right? So it's based on the accumulation of knowledge that have been done before, and it encoded or compressed into some kind of model, right? So how can we harness this prior belief to do Bayesian optimization? Well, the simplest, dumbest, naivest way would be to just use them as feature extractors, right? So here's the example here. So you take a pre-trained transformer here, right? Or LLM from Hugging Face, for example, and then you remove the language modeling head, right? Just remove it, and then put regression head. That's it, right? And then you freeze all the weights of the transformers, and then just do Bayesian last layer regression or GP on top of LLM features, and then you get your beliefs, right? Then it's basically harnessing a prior, right? Just like in a deep kernel learning or like a prior for Bayesian or network and so on and so forth. So it could be that this way of harnessing LLM's knowledge can actually be better than the using classical chemistry specific features that's handcrafted, And indeed, we see that they are actually better. I would like to highlight this the last two here, which is purple and blue. Purple and blue, they are much better than the other, right? Higher is better. And this is average performance in Bayesian optimization for material discovery for different kind of tasks like finding better lasers, finding brighter lasers, finding better battery technology, and then drug discovery, maximizing the docking score, minimizing the docking score, and so on and so forth. And it's the average of all the performance there. And as we can see, LLMs are actually better than FP here. FP is fingerprint, which is like the standard features that people use in chemistry, right? This is the one. And then notice here that LLMs that are pre-trained using domain-specific data, right? Molformer and D5Chem, chemistry-specific LLMs, they are actually much better than orange. And orange here is Llama 2 7 billion, which is general purpose LLM, right? Which is great, right? Because that's confirm our suspicion that LLMs are just prior, right? So for priors to be effective, they need to be close to what we are doing for our task, right? So if we do Bayesian optimization for chemistry, then chemistry specific prior is better, right? That makes sense, right? But can we actually squeeze the performance further? That's the interesting question also, right? In here, can we actually adapt the LLM features to the Bayesian optimization task at hand, right? So the answer is that we can, but nowadays it's still in a point estimation way, right? In the sense that it doesn't have a Bayesian interpretation. So we cannot use it for Bayesian optimization. For example, if you use LoRa or prefix tuning or whatever it is, the PFT flavor that you care about, right? In here, then we want to build a probabilistic model for PFT, right? So PFT here, if you don't know it, it's basically adding like a fraction of weights on top of a pre-trained transformer that's being frozen. And then you just optimize the additional like 1% of the weights of the original transformer. So it's a lightweight way of doing fine tuning, right? But now here, what we have here is a model that looks like this, right? So you have regression head that you need to train and quantify the uncertainty of, because we want to do Bayesian optimization and hence being Bayesian. And then also PFT weights that we want also to quantify the uncertainty also, right? How can we do this? Well, of course, this is the thing that I mentioned before. So the process is very simple. We just take the frozen pre-trained weights as conditioning variable for our posterior belief, right? So our posterior belief is now like this. Usually it's just P of F given D. Now we have an additional conditioning variable, which you can think of it as just a hyperparameter. But the choice of W star, which is the pre-trained LLMs itself, will have an impact to the posterior belief itself, right? So it's just like a prior, but in a kind of different flavor. We do this just simply to make the model probabilistically coherent, okay? But now, even if we have the posterior over W and omega, how do we get P of F given D, comma, W star here? Then we need to compute this integration. And that's hard, right? So what is this integration? Well, this is the distribution that's output by the regression head. So it's the likelihood, basically. So in regression, that means that we have a Gaussian here, right? And then this one here is something intractable, right? This is the posterior over the weights that we care about. And then we take the integral. Of course, that's kind of hard, right? And how can we do this? So two things, right? The first one is how can we get the posterior over the PFT and the regression head. And then how can we do this integration given this posterior? So here we use the linearized Laplace approximation. So the premise is very, very simple. So what we are doing here is to just train the LM or the BFT as usual, just train the regression head and the BFT weights as usual using whatever loss function that you care about, or it should be, should have some kind of probabilistic interpretation, but I digress. And then what you get is just a point estimate, right? Just a single set of weights, right? This, when you do standard optimization, this is what you get, and that's it. Yeah? There is no second step here. But since we want to quantify the uncertainty of our BFT and our regression head, then we need to do something extra, right? So we compute the Hessian of the loss function at this particular optimal point. All right, we come to Hessian. You might think, oh no, Hessian, it's super large, it's hard, right? But it's not. Actually, modern approximation for Hessians are super lightweight, and then they are readily available thanks to second order people, basically people who work on second order optimization. And this is the nice thing about the Laplace approximation, that we can first just take pre-trained neural network and then just borrow tools from second order optimization, and voila, we get the posterior, right? So in picture, what we are doing here is basically, this is the loss landscape, the black one. And then you basically just to run the gradient descent to find an optimal weight, right? So that maximizes the loss landscape. And then you compute the Hessian and then infer it. And then what you get is a Gaussian, right? Centered at this particular point. And the width of this Gaussian is governed by the curvature of your loss landscape. So it's a local approximation. There is you will not capture this probability mass here, but oftentimes it's totally enough. And then how do we compute the integral? Well, it's hard. You can just do sampling, but sampling is just too expensive, right? Because you have to do multiple forward passes over the LLMs. So what we can do is to do linearization. So linearization here over the LM means that we linearize the LM as a function of the weight, right? Theta here, which is omega and W. Not linearizing as a function of x to f of x. That would be dumb, right? So now we have a linear function over the weight, just first order Taylor, basically. And then you have a Gaussian over the weight. So you have a linear and Gaussian. That's another Gaussian, right? For the function output. So this is what we get actually, right? Derivation. I'm not going to talk about the derivation, but just let me know if you need more explanation. So the main point here is that this Gaussian over the posterior output is very explainable, right? So the mean of this Gaussian is just your original retrained or fine-tuned LLM's output, right? That's it. And there is no change, the mean of this Gaussian. But now the only thing that you have is the additional covariance or variance term on top of it. So we are only adding, not changing. And it is quite strong because oftentimes you do a lot of labor to do to make sure that your training of the BFT is super perfect, and you don't want to lose this kind of performance. So the only thing that's the linear Laplace does is that it just add on top of your original prediction a variance term, and that's it, right? Okay, too much math, right? So if you prefer to look at the code, this is what it entails. So we have this library called Laplace Torch, and we will see about it in the second step. But for the first step, it's basically just standard Hugging Face stuff, right? So you just download from Transformer, from BFT, and so on and so forth, And here I use LoRa, for example, but of course, as I said before, it's for general PFT formulation, right? So it's not just LoRa. And you have your train loader, whatever it is, right? In the case of Bayesian optimization, that would be your experiment data from the previous time steps. And then you, train your model, SGD stuff, right? And then when you ask the model with on your test data or to the virtual library in Bayesian optimization, what you get is just a single tensor of prediction, right? So that means there is no uncertainty. That's bad, because then we cannot do Bayesian optimization. But if you do Laplace, just pip install Laplace torch, we get the Laplace, and then just import it. And we do some kind of wrapping, and wrapping is basically just for structuring. There is no cost at all here. And then we call fit. And fit here basically automating everything from the Hessian computation. We basically use some kind of backend from second order library, basically. So Laplace can be seen as a communicating between different fields, essentially. And then do the inversion for you, and so on and so forth. And then when you make prediction, notice that you now have an additional output, which is another tensor that contains your variance of your prediction. And this prediction tensor here is the same as the original one. All right. So I think that's one of the strengths of the Laplace approximation, or especially the linear Laplace approximation. And in fact, because we have a linear and Gaussian models, right? Linear Gaussian, it implies that the linear Laplace is actually a Gaussian process. And if there's if you're more a stats person or math person, then Laplace is actually nice because it's tractable. It's just a linear Gaussian, and then there is a connection to neural tangent kernel, and so on and so forth. So it's it's a nice object to study for statisticians. For computer scientists, for practical people, it's also nice because it's one of the state of the art for Bayesian deep learning. All right, so it's a best of both worlds. All right, so is fine tuning worth it then? It is, right? So here in the solid line or solid curves, we have the standard Laplace, right? On the standard LLM, that's not chemistry specific, right? The red one. And then if you do fine tuning using the Laplace approximation again, we get better performance here, right? The dash one. So it improves performance, but if you already have a strong prior in the sense that you use chemistry specific LLMs, then fine tuning is not that, not that improving performance that much, right? Only maybe here, yeah, whatever, right? So yeah, so that's basically corroborating some the thing that we just discussed, that they are just priors, and the strong prior is desirable. But if your prior is not that strong, it's better to fine tune it further, right? So for example, you have a new task that there is no LLMs for that particular task, then fine tuning is actually can do wonders. All right, to summarize for this first half of the talk, yeah, model discovery is a very important problem in our technological advance as a human. LLM can be useful for this particular task by look at them as just like prior, and then you do Bayesian stuff on top of it, right? And we can also formulate probabilistic version or Bayesian version of PFT in a quite general way for adapting the prior at hand, right? And it can be done with the Laplace approximation, and future work can be not just for Bayesian optimization, but also, any kind of things that depends on Bayesian formulas, any kind of things that depends on uncertainty, right? In terms of Bayesian optimization, future work would be high throughput Bayesian optimization, for example. That's whole different beast, essentially. So yeah, if you have any interest in for science, for scientific discovery, then let me know. So is there any question in this for the first half here?
Okay, I think maybe I have one question actually. So I think one of the things you said was that in terms of the different representation functions that you can use, the choice that you have is that you'll just maybe run the BO process and see which representation is good. So I was wondering, is there some proxy metric that you can also think about to predetermine like what representations are actually good?
Yeah,
for BO?
yeah, that's a good question. There is no proxy as far as I know. The way people do this is that people have like historical data, right, from their own experiments, and you can use this historical data as a benchmark data set, essentially. Well, you have a benchmark data set which basically just like this, just like phi here, but the properties here are real numbers, right? Those are numbers, not just question marks. All right. So it's a data set that's already available, and you can use it as benchmark. Now, given that we have benchmark, then we can just run the Bayesian optimization and then produce plot like this. Then we can do selection, and it's not very expensive to do this, right? Because it's you already have the data. You just query, using pandas and NumPy, and that's it. You don't have to do experiment.
I see. Okay. Yeah, that makes sense.
Yeah. But for specific metrics for it, I don't actually know. People have tried to do, like a what is it called, like a smoothness of the representation, like a roughness. Essentially, if you search on Google roughness, chemistry, molecular landscape, then people have tried to do that as sort of as a proxy for the performance. But for me, it's much better to just run benchmarks because there are data out there that you can use readily.
And that sounds like a hard problem for like high dimensional LLM representations, like to figure out the smoothness of that.
That's true. That's actually true. Yeah.
Any other questions? I think we're good for right now.
All right, then let's go to the second half of our talk, which is actually super related also, because it's still decision making, because we still do Bayesian stuff, because we still do LLMs, right? But the only thing that differs here is how we make decision on which kind of structure we do decision, right? So here we ask slightly different question than just bringing umbrella or not, right? How can we arrive at the office try now, right? So we want to do planning here, right? We want to make a plan. So suppose that the current state is at home, right? And at home, you can make several different actions here. The first one is that you can maybe walk 20 minutes to the subway station. I live 20 minutes away from the subway station, by the way. And then you can call an Uber, and then the next step would be in a cab, and so on and so forth, right? And then given this particular node, we can take another action, right? And so on and so forth, right? And we arrive at the office, then we observe the quote unquote reward, right? Or the outcome. That's relevant to our question. So maybe if you take the train, because there's a 20-minute walk here, then you're not quite sure whether you will be try or not when you arrive. If you take a cab, because you will be inside all the time, well, you definitely try and so on, right? So this is the so-called rollout tree, essentially, right? And then it's basically a decision making still, but on search graph or search tree. And then the goal here is to maximize the terminal reward, right? The reward, the future reward that you haven't seen, right? And you want to maximize this. Maximization here for the particular question would be this one, right? So this is the path that we want, right? So this is essentially planning problem. So we want to find a policy such that we want we arrive at a high high reward in the end. So this is the path that we get. And of course, we also have intermediate reward. If you think about MDP, then of course there's an intermediate reward, right? So to draw a connection about intermediate reward with, let's say, day-to-day stuff, that would be, like imagine that you're working 20 minutes, and meanwhile the cloud is dark and so on and so forth. Oh no, I will be wet. But if even in this case you arrive at the subway station dry, then with high likelihood you'll be dry throughout, because you'll be underground unless there's some kind of flooding going on in the subway tunnel and so on and so forth. Then you will not be dry, right? So given that we arrived at the subway station dry, then we know we have some kind of reward, right? So notice that this kind of things happens inside of our head, right? So we don't actually do simulation, or we don't, well, simulation in our head, yes, but we don't actually, execute all this action and then visit, arrive at the office. Oh, I'm not dry, and then go back home again, and then pick different path. Oh, I'm still not dry, and go back home and so on. It is too expensive, right? So doing this kind of quote unquote rollouts would be very expensive. So this happens in our head, and then we use our beliefs, past experience and knowledge, and the current observation to make decision. For example, if you are currently at the subway station and you believe that subway will always be there will be no flooding going on in the subway tunnel, then you will execute this action, right? So that's something that we human intuitively do when make decision in a split second, right? And so in mathematical sense, what we are doing is doing this kind of problem. It's a planning problem. So we have a search tree or graph, and then you have the unknown here would be your reward, right? The terminal reward, and then the question or decision making that you want to take here is that which given the previous observation, right? Which node should I pick next? Right? So that I maximize our reward. And this decision based on our beliefs, condition on the observation, right? So what would be the application for this? Well, you can do text generation, code generation, protein sequence generation, and so on and so forth. Or you can do reasoning, right? So the tree would be a reasoning steps. If you have heard about tree of thought, people usually just do exhaustive search or do multi-color tree search. But in here, what we can do here is to leverage our beliefs, right, to make decisions. So I'm not going to talk about reasoning. I'm going to use text generation as an example for this particular task. So the question here is that whether we can define our belief for enhancing decision-making foundation models. So this second question is like the reverse direction from the first one, right? So the first one is that we define P of F via foundation model. So it's a forward direction. And the second one here is the reverse one. So we define our belief for foundation models. So that's why the talk title was like a two emphasized word there. All right, so this is a paper by Julia and me, and also with collaboration with other people, Rotian, Ahmad, Philip, and Pascal. And it's about uncertainty guided optimization on large language model search tree. Okay, so let's think about LLM first. Obviously, all of you know about it, but for the benefit of the discussion, I'm going to say that LLM is basically just a next word prediction, right? Where if you put a context or sequence or partial sequence of tokens into the LLM, then what you get is a probability distribution, a softmax output, which is a categorical distribution that lives in a simplex of phi minus 1, where phi is the number of vocabulary in your LLMs. So the size of the vocabulary or the number of tokens that you can generate, right? So this is the example. And if you do this conceptually, I think you are all computer science student, right? And it's not hard to see that what you're doing is actually building a tree, right? In this sense. So the root of this tree is basically your context or x naught here, right? And then at you ask the LM for x1, right? Given x naught. Then what you get is all the possible tokens in your vocabulary, right? With respective score, like the softmax score. And then let's say you pick this one, then you ask the LM again, then you get the same set of nodes with different scores, and so on and so forth, right? Until the maximum depth or the maximum length of the sequence. And a generated text is basically just a path from the root until a leaf, right? So for example, you stop at EOS, then that's just the leaf, right? And in here, it's basically I'm fine, done, right? But which path should we choose? Usually, the common objective would be to maximize the likelihood, right? The log softmax scores along this path, right? Just sum it up. And then we want to maximize this this total likelihood. So we want to find a path in this tree that's maximizing this total likelihood. And this is optimization on trees, right? Just like in our thought experiments, what we are doing was to do maximization on decision tree, right? To optimize the reward. So and you can think of this as a terminal reward here. And the intermediate reward would be the LM output at its node, right? And of course, that's the size of the search space is just humongous, right? Because if you have phi tokens, so phi branching factor, and then you have you want to generate a sequence of length t, right? So that means that your tree is a length of depth tree t. Then what you have is the number of such paths would be phi to the t. And phi is usually like 128,000 for Lamach 3, for example. And t would be, I don't know, 1,000, 2,000, whatever, right? So just too large. So that's why people use some kind of heuristic for this. For example, beam search, which is actually the king in machine translation, right? Or yeah, one of the simplest and one of the best in machine translation. At step, so it's basically, it follows this particle recursion, right? So at step T, we have a B sequences or subsequences like this, for example, we have 2. And then we do expansion, meaning that we ask the LM, hey, what will be the children of these nodes? And then what would be the scores of each of these nodes, right? And then we have many different sequences now, right? That's one more than before. And then we just pick whatever the next sequence that's maximizing the log likelihood or the partial log likelihood, right? So for example, this one and this one, right? This one. And then we prune everything else. Just keep the top P of such sequences. And then we repeat until we terminate, until EOS, right? So we have P many results, and then we pick whatever is the best. So notice that beam search is basically just one more, right? Like a quote unquote one more than before. So it's basically greedy. So in particular, it cannot do backtracking, right? So if we already here and here with beam size 2, then we will not be able to revisit this node, right? And of course, greedy is suboptimal, as you know, right? So we can do better. And molecular tree search can do better, right? So it's a generic planning methods that has 4 steps. The first one is selection. So this is the currently expanded tree, right? And selection means that you want to find a frontier node, a node that's not yet expanded. And how do you do this? Well, you always start from the root, and then you use empirical statistics that I'm going to talk about in the 4th step. And then based on this, we have a Q function essentially that's kind of stochastic. And then so you trade off exploration, exploitation. There's some kind of randomness, and then we and do one-step decision making at a time, and then until you arrive at a node that it's in the frontier. Then you expand. Expand here means that you ask the LLM, you do LLM call. And then you get all the set of the nodes that's possible and the scores, right? And then we do roll out. We pick one of the new expanded node and then do some kind of simulation, or actually you actually call the LLM again and again until you are done at EOS, let's say. And then here you receive the reward, right? You know 100% that this is the reward that we get. And using this score, we basically update the scores that's being used for selection process by just picking up, updating the statistics that we talk about. The statistics are the mean of the reward, and then the number of visits of each node, right? So that's how Monte Carlo research works. And we repeat until no budget left. And notice here we can do backtracking, right? Because you always start from the root, and then you follow this selection process that trade off exploration exploitation. So maybe next time you arrive at this particular node. But the problem with Monte Carlo tree is that it is sample inefficient. Remember that we need to roll out, right? And roll out again, it's just asking the LLM again and again. It's very expensive and so on, right? Remember that you pay OpenAI per number of tokens, right? So that's why you want to minimize this. And then it also has a very slow convergence, right? In terms of the mean and the variance, because think about Monte Carlo integration, which has like a convergence rate of 1/square root of n, where n is number of samples. We can do better. And here is our method called uncertainty guided likelihood research, or OUT. It's basically probabilistic planning, just like in the thought experiments that we have seen before, where we make decisions based on our belief about future reward, right? So we don't actually execute the future, but we make decisions based on what we believe about the future. So the unknown here would be the total reward at the end, but we can also refresh this into, the unknown would be the value of at each node, right? Value in the RL sense, right? So it's like if we, let's say you are this particular node, if we continue go down this subtree in an optimal manner by making optimal decision, what would be the total likelihood that we will see, right? So that's value, right? And what would be the observation? The observation would be, the scores that we have seen in the currently expanded tree in bold here. So that's the plan. We leverage probabilistic inference to make this planning better and without rollout, all right? So the first thing to do here is to assign a prior of our values, right? How can we do this? Because values is defined, if you remember Bellman equation, then it's basically defined recursively, right? So this is basically what we are doing also. We do recursion starting from the bottom, and then we sample from a prior over the softmax. So this is just how we define our prior, specific to our method. So we basically just put a prior over the softmax output on each node, and then propagate this maximum of the softmax outward, so that we get a prior of our values, right? So we sample, and then we basically combine it with the previous the value of the node below, and so on and so forth, and then we go up, right? And recursive bottom up fashion, and then this is sample based, because the maximum Dirichlet, I don't know the cross-form distribution for that, right? So it's much better to use samples, because then you can just sample and then maximize, and so on and so forth. But notice that this is not the same as Monte Carlo tree search, even though what we are doing in Monte Carlo tree search, I was sampling, right? Sampling-based simulation, that is. So this is samples of our prior beliefs, and our prior is basically just Dirichlet. right? So much easier to work with instead of empirical samples. And the output here would be d beta distribution, one for each level of the tree. Why? Because we want to amortize the computation. Because if we store all the samples, oh my God, that's just too much, right? So that's why we do maximum likelihood fit over the samples of the maximum of the 2D slates at each level, and then we make create a beta distribution. And of course, I haven't mentioned it before, but we assume a lot of simplifying things that to make this everything tractable. Okay, now you have a prior that you upload on GitHub or Google Drive, and then you share it on Slack, right? Hey guys, this is the prior. Just do whatever you want with it, right? And this is what you actually do in terms of decoding. So the priors are pre-computed. Now this is the real thing. First selection, just like Monte Carlo research, you start from the very beginning, and then you use the posterior samples now, right? So you have the prior encoded by the beta, and then you combine it with your observation of the score of the softmax that you actually see, right? Just to throw the analogy on the thought experiment, that's basically, I have a belief about whether I will be dry or not. And then I arrive at the subway station and then see things. Of course, I update my belief, right? And then based on this belief, I make decision on which action should I take, right? So that's the analogy. And then we do this recursively until we arrive at the frontier node, just like Monte Carlo research. And then we ask the LLM, right? Hey, LLMs, here's my current sequence. What is the next possible words? And what is the log likelihood? Now we update our posterior samples, essentially, right? The posterior samples, because of all this simplification of the prior, IAD, and so on, is basically the sample from the beta prior that we have obtained before. And then we just combine it with the log likelihood that we have seen currently. And then we take the compute the prior of our values again. So basically taking the recursively bottom up, taking the maximums, all right? And then we repeat until it's unlikely to obtain better sample, or better log likelihood, sorry. So this is the strength of doing probabilistic interpretation. Your belief can be used to make, many different decision making, right? For example, here you stop. Should I stop given my belief and given my observation about the current full sequence that we obtain currently, right? If the probability is small, then yeah, maybe we should continue. But if not, then we should stop, and so on. And notice that we can do backtracking, and then we can combine with the idea of beam search by narrowing down the beam of the node that we expand at each time, right? So it's a best of both worlds. And notice that we don't have rollouts. And in practice, very simple, just replace, Hugging Face generate with our alt generate, and it's compatible with Hugging Face, of course, and you are done. And last two slides, this is basically just to show the performance. So on x-axis, we have average node expansion. So the less, the better, right? Because one node expansion implies asking the LLM. And then y-axis will be the log likelihood. So higher is better. So alt here is better than the other recent baselines here. Okay, in terms of efficiency and in terms of performance. And also it is just another plot with blue score because some people don't like log likelihood, right? And then here's also other, the same plots, but for different LMs, for different data sets. And as you can see here, orange are better than the others, and also blue with different prior, essentially, with alts. And in terms of wall clock efficiency, as you can see, sampling, producing some posterior samples, and also doing, computing acquisition function or the decision, the expected utility, the one that we do for decision making, it's much relatively cheap compared to the forward pass itself, right? So the overhead is just very small. And yeah, that's basically it. And in summary, we've been exploring how can we leverage prior knowledge, beliefs with and combine it with observation to make decision in a tree setting. And especially the application here is the text generation, and being less greedy doesn't have to be expensive, just like Monte Carlo tree search, because whenever you think about not greedy, you think about Monte Carlo tree search or exhaustive search, which are totally bonkers in terms of cost, right? So probability beliefs are much more cheaper than simulation, and it's nice, it's intuitive, but it leads to efficiency gain and performance gain. And future work, for example, with batch version, because the limitation of this work is that it's not batched. So you have to do it one by one. And then for reasoning, then you have to put different priors, then you have a different methods and so on and so forth. Protein sequence prediction for science can also be done in such a way because people also do autoregressive generation for protein sequence. And with that, yeah, thanks very much. It's been a pleasure. If you have any question, happy to discuss.
Right, thank you.
Thanks so much.
So I think we have about 5 minutes for questions.
Thanks, Agustin, for the great talk. At the end of the first part of your talk, where you're computing the posterior, one of the step number 4 you mentioned was linearizing f of x and so on, and that f, I'm assuming, is the LLM, right?
Mm-hmm.
And if so, you have this step because drawing samples requires running multiple forward passes, and that's expensive. Now, the second part of your talk speeds that process up. So what is the interplay between the conclusion of the second part of your talk and step number 4, where now you can efficiently sample the LLM and then use it to get your posterior?
Yeah, good. Yeah, thanks for the question. Yeah, it's a good question. I think there is no direct connection about it, because in here, as you notice here, here we remove the language modeling head, so we don't have any autoregressive tasks anymore, right? So meanwhile, the second part of the talk, it was all about autoregressive generation, right? In here, we don't have anything like that. So in here, we only have a regression head, so the output is just a single number, and that's it, right? Or 2 numbers if you do multi-objective optimization. So yeah, I wouldn't say that we have a connection between those two, because in this case, then we don't have any tree structure.
I guess one more question, maybe related to the previous one, was so in the first part of the talk, you're operating over a fixed set of like known molecules that you wanted to select and then test out. But I guess the inverse design problem would be like, how can you actually optimize to actually generate new unseen molecules?
Yeah.
So in that case, maybe a language modeling head might be useful. And then, so would something like that then make sense to incorporate? And like maybe that's a direction.
Yeah, definitely. This one here is actually the most practical way of doing material discovery. Why? Because we know by definition that everything in our filter library is synthesizable. So we know how to make it, we know how to harness this molecule for our property prediction, right? The other way to do this is to do generative modeling, right? Notice that this is just strings is of the molecule. Then you can just put it into LLMs and then do next word prediction, and then we can use alt, for example, to generate a new molecule. But the problem with this is that based on my correspondence with working closely with chemists, they don't like it because there is no guarantee that you actually can synthesize the molecule. What if the molecules are just garbage, or they are good, but how can we verify that if we cannot synthesize that? Right. So that's the problem. But sure, I think your point is well taken. That's if we can do autoregressive generation that produce synthesizable molecule, and the key here would be retrosynthesis. So that's what you can do in chemistry, retrosynthesis or retrosynthetic planning. Then yeah, I would say that it will be very useful if we can connect them together.
Yeah, I guess I imagine that a utility function might be able to predict synthesizability.
Yeah.
In which case you could.
But there is no guarantee about it, right? Because utility function is basically just our preference. But whether we actually arrive at the solution that's actually synthesizable 100%, then we have no such guarantee.
Yeah, sorry, the mic went off.
Yeah.
No, I think that makes sense. Yeah, I think we're at time. But thank you so much for this wonderful talk. I think this was really exciting.
Yeah, thanks so much. It's a pleasure. If you are interested in any kind of stuff in the future work, for example, just ping me via email. I'm happy to chat with you further.
Awesome. And I think your scheduled meetings will start at 2 p.m. So we'll see you there.
2 p.m. Yeah. See you in our whatever, whoever is the first one.
All right. Thanks so
All
much.
right. Thanks so much. It's been a pleasure.
Bye-bye.
Bye.